Hi, in section 7.7, we're going to take a look at the idea of convolution. So what is convolution? Well, it often occurs that in the process of solving a linear initial value problem using Laplace transforms, we end up with a transform that is a product of two other transforms. So this is what's important. Okay. And instead of using partial fraction decomposition to find the inverse Laplace, we can use the idea of convolution. So what do I mean by that? Well, let's take a look at this. So let's say that we are trying to find the inverse of this. We have 1 over s times s squared plus 1. Okay. Now, this, you can think of it as a product of two transforms. The first one is 1 over s times 1 over s squared plus 1. Normally the way we found the inverse is by doing partial fraction decomposition. That's what we did. We relied on that. But now we can also use the idea of convolution to do this. So instead of doing PFD, so we have two options now to find the inverse. We can do PFD, or we can use the idea of convolution. And convolution works is whenever we are trying to find the inverse of products of two transforms. That's what we mean by that. So we would call this big F, and this would be G, my two transforms, and we want to find the inverse of that. Okay, so that's where the idea of convolution will help us. And convolution is also used to solve a certain class of initial value problems where the forcing function is unknown, or where the differential equation contains an integral. So that's a special type of differential equation called integral differential equation. So we have two different additional types of problems we can solve with the idea of convolutions. Okay, so there's three things we can do with convolutions. Just to recap, we can find inverse Laplace transforms of products of two transforms, where we have products of two transforms using convolutions, or we can use convolutions to solve initial value problem where the forcing function, the external force, is unknown, or we can solve initial value problem that contains integrals, not just derivatives, it also contains integrals. Okay, so there's three things we can do with convolutions. So before we learn how to do those things, let's quickly take a look at the idea of convolutions first. Okay, so let's start by deriving the formula for convolution. All right, so the idea is it helps us take inverse of products of two transforms, right? So let's start with that. Okay, so I'm going to go let big F of s and g of s be two transforms. Okay, so big F of s times big G of s, okay, can be written as what then? We know big F of s is the same as what? Laplace of little f of t, correct? So we can write it that way. So we get Laplace of little f of t, and big G of s is the Laplace of little g of t. We have formulas for both of these, so we're going to write it as 0 to infinite. We get e to the minus st, okay, and then we get f of t dt times the integral 0 to infinite e to the minus st g of t dt. So we're just using the formal definition of Laplace transform. Now, if you remember from Calc 1, anytime you're doing a definite integral, okay, this variable of integration, we always call that a dummy variable. Why is that? Because eventually that variable is going to get replaced with 0 to infinite. So it can be called anything. So I'm going to change that variable because that way we can distinguish between this t here and this t separately. So I'm going to call the first t x. So we get e to the minus sx f of t f of x dx. It's a dummy variable. I'm just changing the name. And this one I'll call y. E to the minus sy g of y dy. Okay. Now I can combine these two integrals and write them as a double integral. 0 to infinite. Add these exponents here. We get e to the minus sx plus y f of x g of y dx dy. So that's what we end up with. So we're ending up with something from calculus 2, a double integral. Okay, so if you haven't had, I'm sorry, not calculus 2, calculus 3. So if you haven't had calculus 3, just bear with me. For those of you who have taken calculus 3, you should be able to follow along easily. Okay, so we want to work with this double integral. So the first thing I'm going to do is I'm going to make a substitution. I'm going to start with the inside integral. Okay, and I'm going to make a substitution for that. So I'm going to go let t is equal to x plus y. So that tells me that dt is equal to dx. Why is that? Why don't we worry about y? Because since we're doing the inner integral, we're going to treat y as a constant. So that'll become 0. Okay. Then x becomes what? If you want to solve, because eventually we'll have to change this x to t, since we're changing everything to t. So it'll become what? T minus y. And I'm going to also change the limits of integration to reflect t. Right now these limits reflect x. I want to reflect t. So what happens if x is 0? What does that tell us about t? If x is 0, t would be y. And if x is infinite, that's the upper limit for x. If this is infinite, we get infinite plus y is still going to be infinite. Okay. So what happens to my product of convolution here? This product now can be written as what? We get big F of s times g of s is equal to the integral 0 to infinite. Now we're going to go from y to infinite. Okay, we're going to get e to the minus st f of t minus y g of y dt dy. So that's what we're going to end up with. All right, next, again from calc 3, we're going to do something called change the order of integration. Currently we are integrating with respect to t first and then y, so we want to change the order of integration. That means we want to integrate with respect to y first and then t. So to do that, we need to figure out a region first so we know how to change it. So let's start with the inner limit. So they go from y to infinite for t. So we know y is less than t is less than infinite. So this implies t is equal to y and then t goes to infinite. Okay, and the outer limit as 0 is less than y is less than infinite. This should be less than because we can't equal to infinite. But just for sake, we can write y goes from 0 and goes to infinite. I'll just put that for now. So if you look at the region right now, what is my region? That's this line. What is that line? That's just a diagonal line. T is equal to y. So I'll call the, y is equal to t, because I'm going to call this t and this y. So we are starting at that line, okay, because we're integrating with respect to t first, and then we're going to infinite. So we're starting at this line and going to infinite in the t direction. So let me use a different color. So we are doing this first. I'll put a 1 here, going to infinite, and then we're going, what does y do? Y starts at 0, that's this horizontal line, and we're going to infinite. So we're starting here and going this way. So that'll be the second integral. So we started t is equal to y, go to infinite horizontally, and vertically we started y is equal to 0 and go to infinite up. So now we want to change the order of integration. What does that mean? So by the way, now that we know where we are integrating, that tells us the region of integration. That's this region we are integrating. Okay, so that's the region we are integrating. So now we want to change the order of integration. So what are we going to do first now? We're going to go up first. We're going to do y first. And then we're going to do t horizontally. Okay. So y will go start at where? At 0 and go to t. Okay. And t will start at where? It's going to start at 0 because that's this point and go to infinite. So that's what's going to happen. Okay, so we get big F of s times g of s is going to be, we're going to go from 0 to infinite for t, and y is going to go from 0 to, it starts at 0, goes up to t. We get e to the minus st f of t minus y g of y dy this time, and then dt. So we change the order of integration. Okay. Since we change the order of integration, this has nothing to do with y, so I can pull it out of that inner integral. So we get 0 to infinite e to the minus st integral 0 to t f of t minus y g of y dy dt. Okay. I'm going to call this inner integral that we have here, this is a special integral, the inside one. We're going to call it something else now. So I'm going to go let this integral 0 to t f of t minus y g of y dt dy, sorry, equal to f star of g. Okay, this is the convolution integral. I'll call just the convolution. So this is my convolution integral. So this is the formula for convolution. Okay. So what does that do to my, hence, to my integrals that we were working with? We had f of s times g of s is equal to 0 to infinite e to the minus st. Now in the inside we get f star of g dt, because we changed that inside integral, this inside one, we call that convolution, so it's called f star of g. If you look at this new integral, that is exactly the integral we would have if we were taking the Laplace transform of this function. So we can write it that way. So we can go Laplace transform of f star of g. So that gives us this f of s g of s. Okay, so we know what the convolution integral is now, and we also know what product of f of s and g of s can be written as now. It can be written as Laplace of the convolution. So from this we can extrapolate a couple different variations just from notations. If I take, so this is one thing to know. If I take the inverse of this, which is what our goal is, to find the inverse Laplace, remember that's what we started with. I want to find the inverse of some product. Okay, so if I take the inverse of this, of big F of s times g of s, product of two transforms, on the right I'll get the inverse of this also, which will cancel, and will just give us the convolution. So this is extremely important. This is the formula we're going to use most of the time, okay, when we do inverses using convolution. So this is the one you need to remember. It's equal to just the convolution integral. Remember, this is the convolution integral. Okay, so let me write one important note. Okay, so actually I'll write two notes. One, from this guy here, okay, I can rewrite this, because what's another notation for big F? It's Laplace of little f of t, and big G is, so we can write this. So we know Laplace of little f of t times the Laplace of little g of t is equal to the Laplace of f star of g. I'm just showing you notation wise. 2. So if we take the, if you look at the convolution integral, it goes from 0 to t. We have f of t minus y g of y dt dy, sorry. Okay, so that's a convolution integral. Okay, so basically what does this mean? It's some type of a translation when you have something changed inside. So we are translating f. Okay, the convolution, it doesn't matter which of these functions you translate. So this is the same as 0 to t f of t g of t minus y dy. So these two are the same. So it doesn't matter whether we translate f or we translate g. So this is f star of g is the same as g star of f. That's what it basically means. Okay, so keep that in mind. So it will not matter which one you translate the two. If you do the integration correctly, both of them will work out exactly the same. All right, so those are the two quick notes on convolution. So things to remember here: remember the convolution formula. This is the formula for convolution. And remember the fact that the inverse Laplace of products of two transforms is the same as the convolution of the little f and little g function for each of those transforms. Okay, so let me give you an example. So let's say that we want to find the inverse Laplace of 1 over s times s squared plus 1. Okay, we want to do that. Now, I can do this problem two different ways. I can use PFD, and if I do PFD, you can remember, if you do the decomposition, what does that break to? We get a over s plus bs over s squared plus 1 plus c over s squared plus 1. You can multiply by the common denominator, then you can set things to 0, you can compare terms, and you can easily find a, b, and c. It'll just take a little work, but we can find that. But now, if you recognize that this transform, this inverse is the product of two transforms, so I can write it as this: 1 over s times 1 over s squared plus 1. Then I can actually use convolutions and find the inverse of this much faster than using partial fraction decomposition. So you have two options now: either use partial fraction decomposition or convolutions. Provided you're working with products of two transforms, you can use convolutions, and you know the inverse of each of these individual transforms. So I'll call this big F, and I'll call this big G. So what is little f of t? If big F is 1 over s, little f would be what? Just 1. And if big G is this, what is little g of t? It'll just be sine of t. Now, what did we learn? We learned that the inverse Laplace of products of two transform is just the convolution. So that means it's the integral 0 to t f of t minus y g of y dy. That's what it is. What is little f and little g? We just know them. They're right here. So f gets translated, but I only have 1, so there's nothing to translate there. So we just get 0 to t of 1. G is just sine t dy. Oops, sorry. It's sine t, but we're using y here, so this should become what? Sine y. So let's integrate that. That's going to give you negative cosine y evaluated from 0 to t. So let's plug in the upper limit. So you get negative cosine of t minus the lower limit. When you plug in 0, we'll get cosine of 0 is 1. This negative will give us negative 1, so this negative will become a positive. So you'll get 1 minus cosine t. So there is the inverse of that. And you can see that was a lot faster than trying to do partial fraction decomposition. Okay. Let's extend the same problem again. Let's say that I ask you to find the inverse Laplace of 1 over s squared times s squared plus 1. Now this one will even get more complicated when we do partial fraction decomposition. Okay, because you know it's going to break goofy. It'll be a over s plus b over s squared plus cs over s squared plus 1 plus d over s squared plus 1. That's what it'll break to. But let's see if we can use the idea of convolutions to do this. So I'm going to break this into inverse Laplace of 1 over, I want to write this as a product. And you always want to write it as a product of two transforms that we already know the inverses of. It makes no sense to write it as a product of transforms whose inverses we don't know. Okay, so we can write this as 1 over s times 1 over s times s squared plus 1. So that's what I'm going to break to. So this will be my big F, this will be my G. What is little f then? If big F is that, it's still going to be 1. What is little g? That means that would be the inverse of this. Wait a minute, we just calculated the inverse of this. It's right here. 1 minus cosine t. So let's use that. 1 minus cosine t. So according to this is just f star of g. That means it is the integral 0 to t f of t minus y g of y dy. That's a formula for convolution. So what is f? F is 1. If you shift it, it's just still going to be 1. And g is what? 1 minus cosine of t. Again, I keep writing cosine of t because this is g of t. That is correct. But we want g of y here, so it should be cosine of y dy. Now we just have to do term by term integral here. Integral of 1 is y minus integral of cosine is sine y, evaluated from 0 to t. So you plug in the upper limit. So we get t minus sine of t. And when I plug in the lower limit, you get 0, and sine of 0 is 0. So just get that. So the inverse Laplace of 1 over s squared times s squared plus 1 is this. And you can see we were able to find that very quickly and easily without a lot of work. Okay. So these are some really good ways to find inverses without having to do partial fraction decomposition. I'll do one more example where you might go, wait a minute, partial fraction decomposition would have been a lot better. So let me do that just for completeness. Not convolution is not always nice and easy to use. Okay. So I want to find the inverse of this. Again, I can do partial fraction decomposition and do it, but let's use convolution. So we get inverse of, the key thing is to break it up correctly. So I'm going to break it up into s over s squared plus 1 times 1 over s squared plus 1. So I'm going to break it up that way. So this becomes my big F, this becomes my G. So big F, if big F is that, what is little f? It's going to be cosine of t. If big G is that, little g would be sine t. So this is just the convolution integral, f star of g, which we know is the integral 0 to t, okay, f of t minus y, g of y dy. So what does that become? F is this, so we're going to have to shift f this time. So we get cosine of t minus y, g of y, g is right here, so it'll be sine of y dy. This is product of sines and cosines. So using a trig identity, the trig identity we're going to use is called product to sum identity. You can look it up in a trig book or in the back cover of a calc book. Product to sum identity, which will give us a half in the front. Okay, actually we could use the product to sum identity and do that. Let me go ahead and show you how we come about with that identity. Okay, so that way we know where that is coming from. Alright, so to do the product to sum identity, we know this, right? We know that, I'll do the identity, so let's just do it. We know that sine of a plus b is equal to sine of a cosine of b plus cosine of sine of b times cosine of a, and then we know sine of a minus b is sine of a cosine of b minus sine of b cosine of a. If we were to add these two together, this would cancel, so we would end up with 2 sine of a cosine of b, and on the left we get sine of a plus b plus sine of a minus b. If you divide by 2, we get cosine of a cosine of b is equal to 1/2. We get sine of a plus b plus sine of a minus b. So that is the identity. In our case, b, in our example, b is going to be t minus y and a is going to be y. Do you follow? So if I do that, what does that integral become? We get inverse Laplace of s over s squared plus 1 squared will become, we get 0 to t, and there's a half in the front. We get sine of a plus b. So you add these guys together, the y's will cancel, so you'll just get t, and we'll get plus sine of a minus b. So you take y minus t plus y, because you subtract this, so you will end up with 2y minus t dy. That's what we'll end up with. Alright, okay, because we'll subtract the y's. Alright, so what do we do next then? We integrate term by term. So let's do that. We're integrating with respect to y. Okay, so we get 1/2. The integral of this will just be, this is a constant now because there's no y here, so it'll just be y sine of t plus, out here you'll have to do a u substitution for the inside, so you'll get 1/2 in the 2 in the denominator, so we'll go u is equal to 2y minus t. Remember, we are integrating with respect to y, t is a constant, so we'll end up with, we'll end up with cosine of 2y minus t, and it'll be negative, so this will be negative, evaluated from 0 to t. So all we did is a u substitution. You'll end up with sine of u, 1/2 sine of u when you do a u substitution, and then the integral of sine of u is cosine, negative cosine of u, and then replace the u back. So now we plug in the upper limit and the lower limit. So when I plug in the upper limit for y, so we get t sine of t, remember we're plugging it for y, minus, when I plug in for cosine here, for y here in the cosine term, I get 1/2, we get 2t minus t is just t, minus, when I plug in the lower limit, sine of 0, this is 0, so 0 times sine of t is 0, minus, when I plug in the lower limit here for y, you get cosine of negative t, but cosine is an even function, so cosine of negative t is the same as cosine of t, and then you have that half. When you distribute this, negative and negative will become positive, these will cancel, so you'll end up with 1/2 t sine of t. So that is the inverse of this. Now the question is, I don't know, you might think this was longer, or I don't know which way is easier. Partial fraction decomposition, I think in this problem would have been easier. The break would be a little bit more complicated. It'll be as over s squared plus 1 plus b over s squared plus 1 plus cs over s squared plus 1 squared, and so on. So it'll be kind of pretty nasty. I don't know, it's your pick of poison here. But you can see how we can use convolutions to find products of transforms. So that was one type of problem we can do. I told you that three types of problems we can solve with convolutions. The next type of problem is that we can solve is referred to as a where the forcing function is not given to us. So let's say that if I give you a problem like this, 4y double prime plus y is equal to g. So let's say g of t. Let's say you're creating an experiment. You're doing an experiment on a mass spring problem. This would be an example of a mass spring problem with no damping and some external force. Okay, but we don't know what the external force is. So you just want to solve this problem for now and then plug in the external force at the very end, you know, once you know it. Or you might want to solve this problem for different external forces. So but then for different external force, you'll have to solve this problem every single time. What if I can come up with one solution and then you can just plug in the different external forces and get the new solutions quickly? So that's where convolutions will come in. It'll let you solve a differential, an initial value problem where you can supply different external forces. Okay, so you can solve it for different external forces without actually knowing that external force to start with. Okay, so the way we're going to do it is just like we normally do, take Laplaces on both sides. So we get 4s squared big Y minus 12s, I'm skipping a few steps, you guys know that you'll be, actually let me go ahead and do them. You get 4s times y of 0 minus y 4 times y prime of 0 plus big Y is equal to big G of s, because Laplace of little g is big G. Okay, So let's go ahead and plug in the initial conditions. This is 3, this is minus 7. So we get 4s squared minus 12s plus 28 is equal plus y. Forgot the y here. Plus y is equal to g of s, sorry. Okay. So we just do like we normally do, solve for big Y. So we get 4s squared plus 1 is equal to g of s plus 12s minus 28. So we're just going to rearrange it. Divide everything by 4s squared plus 1. So we get y is equal to, I'll get 12s minus 28 divided by 4s squared plus 1 plus g of s divided by 4s squared plus 1. Okay. So the next thing we're going to do is do inverse Laplaces. But before I do that, I'm actually going to take a 4 out of this term, out of the first term and the second term. So if I take a 4 out of here, this will become what? S squared plus 1/4. And there's a 4 common on the top, so I can divide both the top and the bottom by 4 basically. So I get 3s minus 7 plus, I'll take a 4 out of here since I can't cancel it with anything. I'll just get s squared plus 1/4. Okay. Alright. So now I can take inverse Laplace here. So we get little y of t is equal to, okay. So what do we get over here? I can split up this. I can take a 3 out. I get inverse Laplace of s over s squared plus 1/4. Okay. Minus 7 times the inverse Laplace of s squared plus 1/4. You know this is sine, so I need 1/2 on the top, so I'll have to divide by 1/2 to offset that. Okay. So keep that in mind. Then what do we need? Plus, I have 1/4 in the front, and then we have g of s. Okay, I don't have room. Times, I'm gonna move this. Just give me a second. G of s times s squared plus 1/4, so I need a 1/2 on the top, so I'll divide this by a 1/2, so there's already a 1/4 here. Okay, so we get a 1/2. We're going to divide by a 1/2. Since we multiplied by a 1/2, we're going to divide by a 1/2. Okay, now I wrote this purposely as a product because we're going to introduce convolutions, because convolutions deals with products of transforms. Okay, so we get y of t is equal to 3 cosine of 1/4 t. Okay, oops, not 1/4, it'll be 1/2 since b squared is 1/4. Okay, it'll be 1/2 t minus this 2 will flip and go to the top, so I'll get 14 sine of 1/2 t. That'll give us that, plus this 2 will go to the top, will cancel with the 4th and become 1/2. And now this, since this is a product of two transforms, what happens? How do we write products of two transforms? How do we write products of two transforms? Okay, we write them as a, when we do the inverse of, oops, did I forget the inverse? The inverse of the products of two transforms is a convolution. So you want to write it as a convolution, and I forgot to put the transforms here, so that's my bad. Let me get rid of this. So we get inverse Laplace of g of s times 1/2 on the top, s squared plus 1/4. So we multiplied by a 1/2, divided by a 1/2 here, and we're taking the inverse of that. So this is just the convolution. So it'll be basically the convolution integral. So we get 0 to t, because this is just f star of g, where f is this function here and g is just big G. Okay, so it'll become what? What is f? What's the inverse of f? what is the inverse Laplace of this? It'll be sine 1/2 sine of, I'm sorry, sine of 1/2 t. So we get sine of 1/2 t, but f is shifted, so it'll be t minus y times g of t dt. So there is your answer. So this is the answer. Now think about it. If you were doing this problem using techniques from chapter 1, someone comes and tells you the forcing function is 4t. You solve it, you come up with an answer. You'll have to use either undetermined coefficient or variable of parameters, okay, variation of parameters. Let's say someone comes and tells you it's ln of t. You'll have to use variation of parameters and come up with a solution, and so on. But by using this technique, we have one solution. If someone comes and tells you g of t is 4t, you replace this with 4t, integrate this, you have a solution. You don't have to solve the entire problem again, like you would if you were doing it from chapter 4, because we would have to plug this in, find the homogeneous solution, find the particular solution, add them up, find C1 and C2 using the initial conditions for this one. If they gave us this one, go back and do the same problem again, find the homogeneous solution, find the particular solution, find the constants again. So that's really tedious. If you're doing an experiment and you want to check your experiment for different forcing functions, having to sit and do the problem again and again for the new forcing function would be really tedious. But by using Laplace transforms and convolutions, we get one answer. All you have to do is just keep changing this function and just having to do one integral. That's all you need to do, and you get a new solution. So that is the whole idea of having undefined forcing functions that are given to you. If you don't know what the forcing function is, we can use this idea of convolutions and come up with a nice answer. Another type of problem that we can solve using convolutions is something called the Volterra integral equations. Okay, so that's basically an equation that involves it's an equation that has integrals in it, and we want to solve that type of integral. Okay, so let's take a look at that. So let's say if I give you this example, y of t is equal to 3t squared minus e to the negative t minus 0 to t y of u times e to the y of t minus u du. I'm purposely using u here since I already have a y here, so there's no confusion. Do you guys follow? So this is called an Volterra integral equation because it's an equation that involves an integral. Okay, so how do we solve this? Well, we'll just do Laplace transforms. We want to solve for y. Okay, so let's do that. So let's take Laplace transform of this. So Laplace of little y is big Y of s is equal to Laplace of t squared is 2 factorial over s cubed. So we get 2 factorial is 2, so we get 6 over s cubed, minus Laplace of e to the negative t is 1 over s plus 1, minus Laplace of this. What's a Laplace of a convolution? So that means we are taking Laplace of f star of g, something like that, correct? That's what we are doing. Okay, out here f, you can think of f as your y term and g as this term, or you can flip them around, doesn't matter. Okay, we do want to treat f as the y, one of these as a y term, okay, just so you know. But what happens? What's the Laplace of a convolution? So let's go back and take a look at that. I've done it. So you can see that here. Laplace of a convolution, okay, is basically f of big F of s times big G of s. That's what it is, Laplace of a convolution. Okay, so keep that in mind. We came up with that formula. So I need to figure out which one's which. So out here, I'm going to call this is going to be my G of t, and this is going to be my f of t, because f of t is translated. Do you guys remember that? And you can translate g of t. I told you, it doesn't matter which one you translate, it's all going to work out. So I have this, I have f, so this is a convolution, so you have f of f star of g. If you recall, that's big F of s times big G of s. That's what it is. So what is big F of s? this is right here. Okay, so what would that be? Because f is basically e to the t, that is translated, and g is just y. Okay, so big F would be what? Big F would be the transform of this, so it'll be 1 over s minus 1 times g. G is y. What's the transform of y? Big Y. Okay, that's what it is. So now we want to solve for y, move y terms on one side. So we get big Y 1 plus 1 over s minus 1 is equal to 6s cubed minus 1 over s plus 1. Okay, you can simplify this by finding the common denominator and doing all of that. So we get s over s minus 1 is equal to 6s cubed minus 1 over s plus 1. Then you divide both, multiply by s minus 1 over s, so we get big Y is going to be, you'll end up with 6 times s minus 1 over s to the 4th, okay, minus, over here we're going to end up with s minus 1 over s times s minus 1, s plus 1. Remember, we are multiplying both sides by s minus 1 over s to get rid of this guy. So we get this. I'm not going to go through this, but if I do PFD, I get big Y is equal to 6 over s cubed minus 6 over s to the 4th minus, we get plus, sorry, 1 over s minus 2 over s plus 1. So that's what we end up with if you do PFD. It's a lot of PFD to do. You have to do this one and this one separately, so it'll take some time, but you can easily do it. And then we do inverse Laplace. So we get y of t is equal to, this is 3t squared minus t to the 3, because that's exactly what it is, 3 factorial over s to the 4th. That's what Laplace of t cubed is, plus 1 minus 2e to the negative t. So we were able to solve this Volterra integral equation. Okay, so to do a Volterra integral equation is basically an equation that involves an integral, and the way we handle that integral is by convolutions, and then you find the inverse Laplace transforms. Okay, the next type of problem, and the last one that we can deal with with convolutions, is something called an integral differential equation. So this is a different type of a problem. Here we have a differential equation that that involves derivatives and integrals. Out here we had an equation that just involved integrals. There was no derivatives. So in this case, an integral differential equation is where we have an equation that has derivatives and integrals. So it looks something like this. So let's say we have y prime minus 4y plus 4 times the integral 0 to t y of u du is equal to t cubed e to the 2t, and they've given us some initial condition y of 0 is equal to 0. So you can see this is an equation that has derivatives and integrals. That's kind of interesting. So it's called an integral differential equation. Okay, so let's see how to solve this. We're going to use derivatives, Laplace transforms. So we're going to transform this. We have only one derivative, not two here. Okay, so we get, in this case, we'll get s times big Y minus y of 0. Y of 0 is 0, so I'm not going to, I'll write it down, y of 0, okay, minus, we get 4 times big Y plus, we get 4 times the Laplace of this function, 0 to t, y of u, and I'll put a 1 here, du, is equal to the Laplace of this. You because we have an e here, you find the Laplace of t and you shift it by 2 units. Is that okay? Laplace of this t cubed is what? 6 over s to the fourth, so it will be 6 over s shifted, so it will be s minus 2 to the fourth, because that's what that translation will come from. So now how do I do this? This is 0. Okay, so how do we take care of this guy? So I'm going to treat this like a convolution integral. This will become my g, and this will become my f. So f is 1, because if you translate f1, you just get 1, and g is just going to be y. So big F is going to be 1 over s, and big G is going to be big Y. Okay, so this can be treated like a convolution integral, so you can think of this as f star of G is what we have. And if you recall, f star of G is what? Big F of s times G of s. That's what we came up with. So now I can rewrite this as, I can take a y out of some of these terms. I get s minus 4. Okay, so far. Actually, I won't take a y out because I'll get another y here. So let's leave it alone for a second. Minus 4y plus this Laplace will become this, which will become this. So big F is what? 1 over s, and G is what? Y. So we get 1 over s times y, but there's a 4 in the front, so we get a 4 is equal to 6 over s minus 2 to the fourth. That's what we get. So you can see a whole bunch of y terms here. Okay, so let's go ahead and pull all of them out. So we get s minus 4 plus 4 over s is equal to 6 over s minus 2 to the fourth. Okay, now we just need to find the inverse. So we get this, we can find the common denominator here, so which would be s, so you'll get s squared minus 4s plus 4 over s, then cross multiply everything, so we get 6s over s minus 2 to the fourth times, okay, we'll end up with what? S squared minus 4s plus 4, which is just same as s minus 2 squared, just so you guys know. So this will become s minus 2 squared. Okay. Alright. So if you wanted to, you can rewrite this right here. This is just going to be s squared minus 4s plus 4 over s, which is s minus 2 squared over s. So when we cross multiply, we get this. So we get 6s over s minus 2 to the 6. You can do PFT. Again, I'm not going to do that. It's going to be an ugly PFT because of that 6. Okay, but if you do PFT, you'll end up with 6s over s minus 2 to the 5. I'm sorry, 6 over s minus 2 to the 5 plus 12 over s minus 2 to the 6. That's what you'll get when you do PFT. So now we just need to do the inverse transform. Big Y becomes little y of t. Okay. Now we have 5 and we have s minus 2. If I didn't have that negative 2, it would look something like this. N would be 4. So you would, if you take the Laplace of t to the 4, you'd end up with 4 factorial over s to the 5. So 4 factorial is 24. So I have a 6. I need what to make it 24? I need a 4 on the top. I'll divide by a 4. So that'll give us this. The negative 2 will just shift it. Do you guys follow? So this will just become what? 1/4. Okay. What do we get? 1/4 t to the 4, and the shift will come from e to the 2t. Okay. Plus, now we have t to the 6. Okay. So what, ignore the 2 for a second. What will give us 12 over, not t to the 6, s to the 6. What will give us that? What transform of what? It'll be some polynomial, right? T raised to something. If it's 6, this is n plus 1, so n would be 5, so this would be t to the 5. But then you would need 5 factorial on the top, correct? So we'll need 5 factorial, which would be 5 factorial is 120. We already have a 12 here, so I'll need to multiply this by a 10 and divide by a 10. So we get 1 over 10. we get t to the 5, and because of this minus 2 it's a shift, we get 2t, and there is the answer to that integral differential equation. Okay, so this is what convolution lets us do. It lets us take inverse of products of transforms like we did. It also lets us solve differential equations where the forcing function is unknown at the start, so we can come up with a generic solution, and then we can just replace whatever forcing function we have, and then we just need to do one integral instead of resolving the problem constantly. Then it also lets us solve a class of two special types of differential equation, special type of equation, one that involves an integral. This is just an equation that involves an integral, and one that involves a derivative and an integral. So those are called integral differential equation. The other one is called the Volterra integral equation. Okay, that's what convolution will help us do.